Let's finish with notes from 7.1, looking at the area between two curves, or between two functions, between two graphs. Uh, Now, from the first page, from the first video, from the first page, we saw that we were looking at graphs that were uh, two graphs that were above one another. So there was a top curve and the bottom curve, but that is not always going to be the case. Sometimes, rather than graphs that are oriented above one another, um, we may sometimes see graphs that are to the left and to the right of each other, across from each other, side to side from each other. So if that's the case, then we have to adapt our area formula a bit. Okay, so if graphs are to the left and to the right of each other, we're going to have to make sure that everything that we plug in is in terms of y. Uh, and so rather than looking for a top curve and the bottom curve, we are now trying to identify the right graph or the right curve and the left curve or the left graph. And now, rather than trying to identify our left and our right bounds, now our bounds will be in terms of y values, so we're looking for our lower bound and our upper bound. So we're basically just taking that area formula and just flipping it on its side. Rather than top minus bottom, we're now doing right minus left. And again, all variables and values have to be in terms of y. Okay, so example 2 is one problem that you can visually see the difference between what we've seen before. So if you look at example 2, it says find the area of the region bounded by y is equal to plus or minus root 2x minus 2. So here's positive root 2x minus 2, and here's negative root 2x minus 2. And the linear function y is equal to x minus 5. So here's y equals x minus 5. Okay. Now if we look at these graphs, okay, we can treat this like one graph. Okay, and the second function, second graph, is with this linear y equals x minus 5. This is no longer a top and a bottom graph because now there are regions where we see that this curve is above the linear function, right? But then it's going to get to a point where it's not going to always be consistent, because as we move further left, we see that the top curve in this region, right, the top curve in this region is going to be the positive root 2x minus 2, and then the bottom is going to be the negative root 2x minus 2. So the bottom curve is not consistent throughout this entire shaded region. So the top minus bottom is not going to be a relationship that we can use if we want to write it in one formula. We're going to have to think of it in terms of a right graph and a left graph, because this line for this entire interval, this line is always to the right of this curve. So this is consistently the right curve, and this is consistently the left curve, as long as we're comparing to values that are directly across from each other or sideways from each other. Okay? And because everything has to be in terms of y, we have to convert our equations, because right now our equations, if we plug this in, this would be in terms of x, and that would not be the appropriate form for if we want to find the area using looking at it from a sideways from in terms of y. So we have to solve for in terms of x so we can get our equation in terms of y. So we basically have to solve for x. Okay, so we take this, we square both sides. Y squared equals 2x minus 2. Therefore, y squared plus 2 is equal to 2x. Solve for x by dividing both sides by 2. So we get x equals 1/2 y squared plus 1. So this 1/2 y squared plus 1 will represent the sideways parabola that we see here. Okay, and this will be considered the left graph. The y equals x minus 5, we want to solve for x, so x equals 5 plus y. So 5 plus y will represent this linear graph that you see here, and this this linear graph will be our right graph. Okay. We need to find the points of intersection because we need to find the bounds. So the way we do that, we set our two equations equal to each other, the 1/2 y squared plus 1 and the 5 plus y, set them equal to each other, bring everything over to one side. And if I want to factor, I want to first get rid of that 1/2, so multiply everything through by 2. And I'm left with y squared minus 2y minus 8, which factors to be y minus 4 and y plus 2. And we have our y values, 4 and negative 2. These are our bounds. So our lower bound will be the negative 2, and our upper bound will be the positive 4. So we just plug this in our formula here. Negative 2 is our lower bound, 4 is our upper bound. The right graph, 5 plus y, our left graph, 1/2 y squared plus 1 dy. Notice everything that we're plugging here is in terms of y. You don't see any x's. If you're trying to do right minus left and you have an x in here, or you're using bounds that are in terms of x, then you have to go back and look to see how to make that adjustment to make it correct. So we just now try to combine like terms and apply a power rule to find the integral and to find the definite integral. So this reduces to be 1/2 negative 1/2 y squared plus y plus 4y. All the parentheses are gone. We combine all the like terms that we could. Now we apply power rule. So negative 1/2, we get y cubed over 3 plus y squared over 2 plus 4y. Evaluate between our upper and lower bound. Plug in your upper bound first. So 4 plugs in for every y value that you see. All right, and then minus. Now we plug in the lower bound in for every y value that we see. And then we simply just combine these like terms, combine all these terms together, and we get positive 18 as our area. Okay, again, since we're using area formula, we should always get a positive number. If you're getting a negative answer, then you have to go back and look to see what you did wrong. Okay. All right, one final example here. This is a graph where we see an f of x graph here, f of x curve, and then using dotted line, dashed lines, I graphed, this is the g of x graph. Okay. If we want to find the area, we will not be able to use top curve minus bottom curve. We can't use just one formula because, as you can see, the top curve and the bottom curve will alternate depending on which interval we're talking about. So because of that, we have to think of it as 3 separate definite integrals. Okay, that way we can ensure that we find the area for each region, because each region has its own top curve and bottom curve. So then we just treat it like 3 separate problems. The first region would be left bound would be A, the right bound would be B. So that's from A to B. Top curve is f of x, bottom curve is g of x. So that would take care of the area for my first region. For my second region, we see that the top and the bottom curve have alternated. So my g of x is now my top curve, and my bottom curve is now the f of x, and the bounds are now from B to C. And finally, we have our third region, which is from C to D. And again, it alternates back to f of x being the top curve and the g of x being the bottom curve. So we have f of x minus g of x, definite integral from C to D.